normal distribution. This is more well known as the bell curve. What's the bell curve? It's like there's an average, and then around the average you have this bell-shaped curve, right? Now, among all the bell curves, the one that we are going to call as the standard normal distribution would be something that will have the average as 0, and well, standard deviation tells you how wide the distribution is, right? And what's going to happen is that you're going to choose the distribution that has wideness of 1. That's a bit hard to describe, so I guess one standard way to say it is like the standard normal distribution is where if you go 1 and -1 and you look at this probability, the probability of this point is about 68%. About. That's called the standard normal distribution. Of course, if you have wider ones, then you'll have less things captured inside this. If you have a narrow peak, then most of the data will be inside 0.68. Inside the -1 to 1, more than 68%. So the one that has about 68% of the data inside -1 to 1, that's called standard normal distribution. Okay. So the formula for this is something like e to the negative x squared over 2. Let's just forget about over 2 and think about what this means. What is e to the negative x squared? What's the graph of this? If you plug in 0, what do you get? 1. As you plug in something higher, what happens? It goes down, right? Yeah. It goes down pretty quickly. And it's symmetric. If you plug in -1, the value is same as plugging in +1 because of this x squared, right? So you can kind of see that the graph quickly goes down to 0, giving you some kind of a bell curve. Now it turns out that it's not this one that you want. You want the division by 2 if you want the standard size, standard normal distribution. Okay? So that's what we want to show. Okay, so what I want to show is that the normal distribution, the standard normal distribution will be this one with some unknown constant. Let's figure out what this constant is. How do you figure out the constant? If you have this unknown constant coefficient, what determines what this coefficient must be?
Solve for a value?
No. It's an important property of a probability density function. What is it?
The average.
What?
The average.
Not the average. What? No, not the peak. Peak could be high or low, it doesn't matter. There's one property that two properties, in order to become a probability density function, number 1, it has to be positive. Number 2, it has to equal 1 if, not the sum, we're doing integrals, okay? You add if it's a discrete probability distribution function. This is a continuous distribution. So in that case, you have to integrate to get the probability, right? Yeah, so what do you do?
Integrate.
Integrate from where?
0.
Oh, see, in its domain, okay? If the probability distribution is the entire line, then you integrate over the entire line. Some probability distribution, like the uniform distribution that we were doing last time, it was between two numbers, okay? The exponential distribution that we did just before this, it was defined from 0 to infinity. So for example, this distribution here, if you integrate from 0 to infinity, you will see that this gives you 1. Okay? Yeah. It's a simple integral. You can try to see if it's true. Okay. So, to figure out what this is, we need to know integral of c times e to the negative x squared over 2 dx from negative infinity to infinity. It has to be 1. Okay? In other words, I can pull this c outside and divide and say 1 over c is the value of the integral of the bell curve. It's this thing. The problem is that this integration is called the Gaussian integral. It's not a straightforward integral. There's no u substitution you can use to do this integral. You can try to set u as this thing and try as you can, all you can. It's not going to be doable. All right, so let me show you a nice trick that every engineer should know. This integration is called the Gaussian integral, and therefore it appears in physics, it appears in math, it appears in engineering. So many places you're going to see this. So you should really try to learn what this is. Okay? So let me call this value 1 over c squared, and that means I have to multiply 2 of these. But then, because I want to combine this into a single double integral, I'm going to call write this second one in terms of y instead of x. Okay? Now I'm going to put this inside. That's going to be this is just a number, right? So I can pull it inside the integral. And I can now say, oh, that has nothing to do with this dy, so I can put this inside as well. So now this becomes a double integral. In other words, you cannot do this integral if you just did Calc 2. You have to use Calculus 3, multivariable calculus. Okay, and from here to there, I'm using the fact that e to the a, e to the b is e to the a plus b. So I'm just adding these two. What is this? This is a two-dimensional bell curve. So if you had the graph of z equals to e to the negative x squared over 2 minus y squared over 2, that's like a surface where this will have the value of 1 at 0, 0, right? It will have the biggest value. But then as soon as x and y increases, as you go off the center, it goes down. So you have a three-dimensional, nice bell-shaped thing. If you took any level curves, it will be circular. So it will be some kind of a Mexican hat? No, that's a bit different. Some kind of like a bell-shaped thing. It's going down quickly. Okay. All right. So that's what you're integrating over the entire domain. And then looking at this, I see that this looks like e to the negative 1/2 x squared plus y squared dy dx. And if you have x squared plus y squared, that reminds you of r squared equal to x squared plus y squared, right? What is that? Where is that from?
Equation of a circle.
No.
For a sphere.
R squared equal to x squared plus y squared. This is from the polar coordinate system. Okay? So, wow, I'm curious how many of you remember that. dy dx is the way you do area integral, right? What's dA in polar coordinate system? Does
dr d
anyone-
theta.
Huh?
dr d
Yeah,
theta.
like the
Huh?
could be, it's like d theta and then you have.
Okay, so dr d theta, you're missing something still.
R squared.
No?
Z?
No?
Oh no, it's just R. Isn't
It's
it?
just R. It's just R. Yeah. R dr d theta.
Obviously.
Okay. You knew that, right?
Yeah.
Yeah, everyone knows that. Yeah. Okay. All right. So, so what you do is in the polar coordinate system, if you see dx dy going infinity for both gives you the entire two-dimensional plane. But if you want to represent the entire two-dimensional plane using r and theta, here's how you do it. Theta goes from 0 until
360.
2 pi. You use radians in calculus. You don't use degrees, okay? All right, and then r goes from
2 to 1.
0 until infinity, right? So what you have is the integral from 0 to infinity for r, and then integral from 0 to 2 pi for d theta of this object e to the negative 1/2 r squared, because x squared plus y squared is r squared. And then dy dx is now changed to r dr d theta. Now this integral is now easily done because, look, if you differentiate the inside function, you get negative r, right? So, I don't want to erase this. Where should I'll erase here. If you take e to the negative 1/2 r squared and you differentiate by r, this doesn't change, but then when you differentiate the inside function, that becomes negative r. So if you put a minus in front with a minus here, then this much is just the derivative of e to the negative 1/2 r squared. So that's going to be negative e to the negative 1/2 r squared, r going from infinity and 0, and you still have to integrate from 0 to 2 pi for d theta. Okay? Here's your unofficial homework. I'm not going to grade it, but go home and try to recreate this without looking at the notes. No, I'm not joking. It's like basic knowledge for any engineer. Okay? If you want to call yourself a real engineer, you should be able to draw, take a blank piece of paper, and you should be able to start from here and say this squared is this, and then you do all that and get this answer. All right. So if you plug in infinity, what do you get? 0. If you plug in 0, what do you get? 1. But because you're subtracting a negative 1, it becomes a positive 1, and you integrate from 0 to 2 pi d theta, which integrates to theta. You plug in 2 pi and 0, and that gives you
2 pi.
2 pi. So therefore, this value is 2 pi. What's the value of c? Oh, no. That's 2 pi, so square root is square root of 2 pi, okay? So here's what we just found. We just found, after all that calculation, that 1 over c must be square root of 2 pi. Is that okay? 1 over c should be square root of 2 pi. It's because this squared is 2 pi, it's either plus or minus square root of 2 pi, but it has to be positive because this integral is positive. It can't be negative. So this is positive, and that means c must be 1 over square root of 2 pi. Okay. So all this calculation showed you the following. all this calculation showed you that f of x equals to 1 over square root of 2 pi e to the negative x squared over 2 is a probability density function. That's our conclusion. How do we know that? On negative infinity to infinity. How do I know that? That's because this is positive, right? On negative infinity to infinity. And if you integrate this function from negative infinity to infinity, it's going to give you 1. That's because this is fine-tuned so that the integral will give you 1. Is that okay? All right. And that's called, this one is called the standard normal distribution. And it's the one that's used most frequently. It's the most important. If I only had one continuous distribution to just repeat over and over because nobody's getting anything, then this would be it. I'll just repeat this one distribution and talk about this the entire semester. Hopefully that's not the case. But this is how important it is. Right? Okay. Now, let's do the second, the two other things. I want to know expectation value. How do you do this? You integrate negative infinity to infinity of what? X times the probability distribution. This is what you have to integrate. Okay. And this one, this one's just simply 0. Now, why is it 0? Well, first of all, as I said, the shape is a bell curve centered at 0. So the average is obviously 0. So you can just say it's 0 without even doing any work. But if you wanted to make an argument with this integral, you can say, well, this is what we call an even function, right? Plus value and minus value are the same. But what does this do? That's an odd function. If you multiply an odd function with an even function, what do you get? You get an odd function, right? So if you integrate an odd function over a symmetric domain, you get? 0. You remember even and odd, right? Even functions are the ones that, if you have something that folds nicely, that's called an even function, right? But if you have something that goes up on one side, it goes down the other side, then that's called an odd function. Odd function has this symmetry where if you integrate over a symmetric domain and one goes up, the other goes down, and these two cancel. So that integral is 0 without doing any work. All right. So that's that. What about the variance? Well, the variance would be you would have, what is this? This is e of x squared minus e of x squared. But we just found out that this is 0, right? So we just have to do this one, which is integral from negative infinity to infinity of x squared times 1 over square root of 2 pi e to the negative x squared over 2 dx. Now this is suddenly, again, impossibly hard. It's as hard as trying to do this in math. Yeah. Okay? It's as hard as
X squared.
So now I'm going to show you something that you don't have to know. I really want everyone to know how to do the integral of this, okay? But let me just show you something that you don't have to know. But still, if you try to understand as much as possible, if you say you can understand, like say 70% of what I say, that should be good enough. You'll be able to understand what's going on. But if you don't understand it, maybe you can still do well on the exam, but you'll be kind of miserable not knowing what's happening. Okay. All right. So there's this trick where you have the following observation. let's think about this interval. I know that if you integrate this, you get a 1, right? But let's say you have a t as 1. What happens to the graph if you have, instead of x, x minus 1?
It gets shifted to the
It
left.
shifts 1 to the right, right? Yeah, shifts 1 to the right, okay? But you're still integrating the graph from negative infinity to infinity. What do you think the area would be?
I'm gonna be the same.
It will be the same because whether you integrate this from negative to infinity or you move everything to the right and you integrate from negative to infinity to positive infinity, it'll still be the same. It'll still be 1. Don't you think? Right?
Mm-hmm.
Okay. Do you agree? All right. So now here's the interesting stuff. Try to expand this and write it like this. If you have well, if you just expand this, this is x minus t squared, this x squared minus 2xt plus t squared, right? So it will be plus xt minus 1/2 t squared dx. Is that okay? Yeah. T minus x squared is, or x minus t squared is x squared minus 2xt plus t squared. So all I did was I just replaced this top by that and expanded. Okay. 1/2 and 1/2 cancels. That's why there's nothing in here. Okay. Then I see that since we are integrating by x, this t has nothing to do with the integral. So this one, when we write it as just like this, right? Multiplication, the sum of exponents is the same as multiplication between exponents, right? And then this one, I claim that since this has nothing to do with x, this is like a constant which I can pull outside the integral. So I have e to the negative 1/2 t squared, negative infinity to infinity, of 1 over square root of 2 pi, e to the negative 1/2 x squared plus xt dx. And then, remember, what is this equal to again? This entire integral. It has to be equal to 1. So, I just multiply this to the other side. And here's a result that we just immediately get, which is the immediate result is that if you integrate from negative infinity to infinity of 1 over square root of 2 pi e to the negative 1/2 x squared plus xt dx is going to equal to e to the t squared over 2. Notice that this negative exponent means what? 1 over e to the positive 1/2 t squared, and then if you multiply to the right side, now this becomes positive exponent. Okay? All right, so that's a nice result, but what does this have anything to do with integral of x squared against this? Well, here's a nice idea. This is a function, you're going to view both sides as function of t now. See, the x is already integrated out, so this entire integral depends on t. So does the right side. Which means I can differentiate both sides by t. Let's see what happens if we do that. If we differentiate both sides by t, exponential functions don't do anything if you differentiate, but then the inside has to be pulled outside and you have to differentiate the inside function by t. What do you get if you differentiate this by t?
X.
Just x, right? X is the only thing, right? So you get x, 1 over square root of 2 pi, e to the negative 1/2 x squared, plus xt dx, equals to, if you differentiate this by t, it's t times e to the t squared over 2. Okay? Now plug in 0. That goes away, right? What is the left side? If this is 0, this is something that we've seen before. What is it? This is gone. What is it?
Oh, it's.
1 over c.
Yeah, it's no, not 1 over c. No.
Z of X.
E of x. Yes, it's e of x. Isn't that right? Yeah, this is e of x, right? Now you plug in t equal to 0 over here. What do you get? 0 times anything is 0. So we've just shown that e of x is 0 just by plugging t equal to 0. But that's not what we want. We want e of x squared. So what should we do?
Square.
No? What should we do? How do you get e of x squared? To get e of x squared, we better be integrating against x squared times 1 over square root of 2 pi. This is what you want, right? How do you get this?
Multiply both sides.
Nope. I showed you this one trick. You should apply it again. What? Huh? No.
R's and thetas.
What?
The R and the theta.
No, not that.
That you like put it inside the other integral?
No, they didn't. Okay, so
Oh, is it the exponential trick where you...
no, that's not it.
U substitution.
No, there's so many techniques here. Okay, but you're failing to get that one thing. Somebody raise their hand. Do you,
You say differentiate by t then?
yes, differentiate both sides by t. That's what you do. You differentiate both sides by t again. What happens then? Another x comes down, and you get x squared. So you're going to get this one, right? But then to get this, you better plug in t equals to 0, right? But that means we have to differentiate this side by t as well. Do you agree? But when you differentiate this by t, this time you better use the product rule. Isn't that right? Yeah. So you differentiate using the product rule. It's 1 times e to the t squared over 2 plus t times e to the t squared over 2. And then you have to plug in t equals to 0. Okay, now look. You plug in 0, what happens to this? 0. What about this one?
1.
1. But what was this again? This was our v of x. That was our variance. Okay? So the variance, so here's what we just proved. So let's recap this. So from this one, from this identity, we figured out that this is true, okay? And then by differentiating this twice, both sides, and then plugging t equals to 0, we were able to find that the variance is 1. What's the standard deviation again? What is the standard deviation? No?
CE and the negative x squared over 2.
Standard deviation is the square root of the variance. Okay? Standard deviation is the square root of the variance. So you have the square root of the variance as 1. That's what we just found out. So here's the, after all the hard work, here's what we found out. Okay, so what we achieved today. Number 1. Is a PDF. We found that out, right? Because if you integrate, you get 1. Number 2. If a random variable, continuous random variable follows this distribution, the average will be 0. The mean value will be 0, okay? And number 3, the variance is going to be 1, which also means that the standard deviation, which is the square root of the variance, is also going to be 1. Okay? That's why satisfying the mean equals to 0 and standard deviation 1, this is going to be called the standard normal distribution. Okay. You got that so far? Somewhat? Okay. So now let me do a conclusion by just discussing some results. And here's a question. Okay, this n is for normal. Normal distribution has two parameters, average and standard deviation. So when I say n01, I mean this function. Okay? So I have this function. And the question is, what is the chance that if a random number is generated from this distribution, that the number that you see is going to be between 1 and 2? Is that okay? All right. Now, how do you write the answer? Answer would be, you take the integral from 1 to 2. That's how you get the probability from continuous probability distribution, right? Yeah. Except that we've already seen how challenging this is to integrate. So there's no way you can do this integral. Okay? When it was like 0 and infinity, those are possible by using all these very hard math. Okay? But even those kind of hard math won't be able to give you the exact value of this. So what was our mathematician's solution? That was the solution is to come up with a table. People would do the numerical calculations and make a table of values. So the way you're going to use this table is like the following. The table doesn't have two values. Instead, it has the integral from negative infinity. So this here is same thing as integration from negative infinity from 2. Let's just call this f. Okay? Fx. F of x dx minus negative infinity to what?
1.
1. Because then, see, here's the bell curve. Here's 1, here's 2. We want this area. How do you get this area? You take from negative infinity until 2 minus negative infinity up until 1. If you subtract those two values, then you get the value, right? So that's what you do. And then, once you have this, then you look at a chart. I tried to print this out, but my printer failed. Sorry. So, but let me just write down this value from the chart. If I look at 2.0, it gives you 0.9772 minus 1.0 is 0.8413. And whatever that value is, that's going to be 9, and then 5, 3, and then 1. 0.1359, which means about 13.6% of the data or of the random values will fall between 1 and 2. That's what we mean. So that's going to be, in the future, you're going to have these word problems where the answer is not obtained by doing the actual integration, but rather you have to find from the chart. That's what you do.